Hi, I'm Eric. You may know me from such short films as, "Hey, was that guy my TA like 10 years ago?" And talking in a corner of a party about how much you didn't like math once we added all those letters to it. Here at we take the safety and well-being of our dogs very seriously. That's why Chunk and Walnut have a motivational coach on hand, and it's why we always have trained stunt doubles on set in case we ever run into any situations that might be difficult or unsafe for our actors. I hope you've come to notice that we're really trying to build like an intuition for how to think about topology as we've been working through these episodes. One of the mantras that I've mentioned several times at this point is that you want to be thinking about topologies as describing some sense of closeness in your set. We've already said that we should be thinking about open sets as like bundling points that are close together, but that intuition is not at all obvious from the definition. Though to be fair, a lot of intuitions aren't clear from definitions. And we even saw last time that if we're going to try and draw and visualize things, like for instance the subspace topology, then points close together remain close together in the subspace topology, because of course they do. You're just zooming in. But now the question becomes, how do we make this intuition gel with what happens when we actually sit down and do math? So, continuing this discussion of closeness, let's try and make that wishy-washy idea a little bit more precise. How exactly do topological spaces and open sets give us a notion of proximity? It's a notion we've been championing for a while, but I've yet to really give you any good reason to believe why this should be the case. And it's certainly not okay to just draw pictures and say, this point is next to that point, because that's not math. So what are we to do? The main ideas are going to be the concepts of limit points and convergent sequences. Let's work our way up to these concepts and then explain why they describe nearness. First, let's get some preliminary definitions off the ground. Say I hand you some topological space X and some set A inside of X. As we've seen, it could be the case that A is open or not, or closed or not, or both or not. No matter what A I hand you, we can take the interior of A, int A, which is just the largest open set inside of A. It's the union of all the open sets inside of A. We can also take the closure of A bar, which is just the smallest closed set containing A. It's the intersection of all closed sets containing A. It's a homework exercise that if A is already open, then the interior of A is just A itself, and if A is already closed, then the closure of A is A itself. But if A is not already open, then the interior is a set distinct from A, and if A is not closed, then the closure too is distinct from A. But as with most definitions, the interior and closure are kind of easy to think about abstractly, but sort of messy to actually write down right now. If you hand me some set A, how am I supposed to conceptualize every closed set that contains A, let alone take their intersection? So, to that end, we have the aforementioned definition for thinking about, and the following theorem for writing down. Let A be a subset of X. A point little x lives in the closure of A if and only if, for every open set U that contains X, U intersect A is not empty. To start to prime your brain to think about things in terms of nearness, we're going to call open sets that contain X neighborhoods of X. Okay, hang tight, because the very first thing that we're going to do is negate everything in sight in the theorem, because it's a lot easier to prove something is not the case than it is to prove that it is the case for infinitely many possible open sets U. So we're going to prove let A be a subset of X. A point little x does not live in the closure of A if and only if there is some neighborhood of X, call it U, such that U intersect A is empty. So this is the same theorem, but it's going to be easier to show it this way. The reason we didn't start here is because the theorem as originally stated is easier to use. So it tells us when points live in the closure of A as opposed to when they don't. So let's prove. In one direction, assume x isn't in the closure of A. We need to cook up a neighborhood of x that doesn't intersect A. Here's a good one. X minus the closure of A. That's open because the closure of A is closed, contains x because the closure of A didn't, and doesn't intersect A because A lives in the closure of A, which was tossed out. Great! In the other direction, assume we found a neighborhood of x that doesn't intersect A. Call it U. Then x minus u is closed, and also it contains A because u didn't touch A at all. And since x is in U, x isn't in x minus u. But the closure of A is the smallest closed set that contains A. So x minus u has to contain the closure of A. So if little x isn't in x minus u, then it can't be in the closure of A either. Fantastic. Cool, we now have a classification theorem. We can now say when points do or do not lie in the closure of a set A. They will exactly when their neighborhoods can't help but intersect A. Yet again, we're seeing the language of closeness inform our understanding of topologies. We can actually go a step further though. Let's now get to finally describing limit points. Again, let's say I hand you some set A inside of a topological space X. We'll define a limit point little x of A to be a point where every neighborhood contains a point in A minus little x. So x may or may not be in A, but every neighborhood of x does at least intersect A at a point other than x itself. And based on the theorem we just did, x is a limit point of A if x is in the closure of A minus x. And just for notation, we'll use A prime to denote the set of the limit points of A. Okay, neat definition. What can we use it for? The closure of A is A union its limit points. This theorem gives us yet another classification for the closure of A. This proof is straightforward enough that you should really take a stab at it yourself if you're feeling up to it. It follows straight from the definitions and Theorem 2, so just use a double inclusion argument. If you want to pause, have at it. If not, here we go. First, suppose x is in the closure of A. We need to show that x is in A or the limit points of A. Well, either x is in A or it's not. And if it is in A, great, we're done. Fantastic. But if it's not, well then since x is in the closure of A, by Theorem 2, every neighborhood of x intersects A. But A is the same set as A minus x because x isn't in A. So by definition, x is a limit point of A. Hooray! Second, suppose x is in A or the limit points of A. We need to show that x is in the closure of A. If x is in A itself, then we're done because A is a subset of its closure. If x is a limit point of A, then every neighborhood of x intersects A minus x. By Theorem 2, x is in the closure of A minus x, and the closure of A minus x is contained in the closure of A. So x is in the closure of A. Ta-da, that's it. And as a quick corollary, a set is closed if it contains all of its limit points. Yet again, we see that topology is describing nearness. Now we're going to move to part 2 of today's discussion. It's actually a separate way in which topologies describe nearness. The basic idea is that of a convergent sequence. Again, we need to lay down some groundwork, so first let's describe what a sequence is. For us, a sequence is just a list of points in our space. x1 is the first point, x2 is the second point, x3 is the third point, and on and on and on and on. A sequence is just a countable list of points. If we wanted to be sophisticated, we could say, it's a function from the natural numbers to our topological space. But that's a little bit overkill. Okay, so there's a sequence. Now, what does it mean for a sequence to converge? Let's give some intuition first before we actually give the definition. In the real numbers, a sequence converges to some number L if we get closer and closer to L, the further down the sequence we go, more or less. And there we go. We've gone and stepped in it again. No, that wasn't chunk and nut. We've stepped right into the idea of nearness again. Another way to describe convergence in the real numbers is that the tail of our sequence gets arbitrarily close to L. So let's take this real numbers definition and say it in enough suitable generality that it applies to any topological space, not just the reals. A sequence x1, x2, x3, yada yada yada, converges to a point little x if, for all neighborhoods u of x, there exists a number capital N such that if little n is greater than or equal to capital N, then x sub little n is in U. What this says in plain English is that a sequence converges to x if you hand me any neighborhood u of x, and I can pick some point at which the tail of the sequence forever stays in that neighborhood. Do you remember when we first started, and I mentioned that every time we see a new definition, we should compare and contrast it against the real numbers? That's super important to do right now. Here's a real intuition breaker. Let's consider the following topological space. Here's a topological space with just 3 points. What's the worst that could happen? The bubbles indicate non-empty open sets, as we've done in the past, and you can check for yourself that this satisfies the definition of a topology. We'll talk about sequences on this space in a second, but first, just notice that the singleton B isn't closed, because AC isn't open. That should already feel a little weird. In R, singletons are closed, because their complements are just disjoint open intervals. But that's not even the worst of it. Let's think about the sequence B, 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 on and on and on, constantly B forever. If there's any justice in the world, then this sequence should converge. And it should converge to B itself. And that much is true. We can check it. No matter what neighborhood of B, no matter what circle containing B you choose, the sequence will stay inside that circle, because the sequence is just the point B, B, B over and over and over again. But if there's any justice in the world, the sequence shouldn't converge to A or to C, right? I mean, we've already seen that it converges to B, so pack it up, call it a day, we're done here. That's all there is to it. Right? Right? No, of course there's no justice in the world. Everything is a hell world, a nightmare of consumption. The planet is hot and the wealth is hoarded, and unfortunately our intuition breaks here. In fact, the sequence B, 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 yada 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 converges to B, but it also converges to A and to C as well. Let's check with the definition. To see that it converges to A, pick a neighborhood of A, like this one. Does the tail of this sequence stay in this neighborhood? Yes, because B is in this neighborhood. What about the only other neighborhood, this one? Again, the tail of the sequence stays in this neighborhood. Every neighborhood of A contains B, so every neighborhood of A contains the tail of the sequence. Those are the only neighborhoods of A, so by exhaustion, the sequence converges to A. And by complete symmetry, the sequence converges to C as well. There's no functional difference between A and C in this picture. Ugh. Ugh. Yuck. Ugh, what is this? It's an awful taste in my mouth. That's the taste of something breaking our intuition. Something not behaving like R. And whenever that happens, we want to sweep it under the rug, like the questions we ask on Math Stack Exchange. What this means for mathematicians is that we ought to give a definition of a topology where things like this don't happen. We'll call a topological space Hausdorff if you can hand me 2 distinct points, and I can find neighborhoods of each of them that are disjoint. Here's some final homework for you. Show that this definition of Hausdorff fixes that gross taste. You can show that in Hausdorff spaces, singletons are closed, and if sequences converge at all, then they converge to only one point. Thank goodness. Hausdorff spaces are pretty much the bare minimum structure that you want to impose on top of being a topology to get any sort of interesting theorems. So most of the topological spaces that mathematicians tend to think about tend to be Hausdorff, with one major exception. Hang on. Yeah, I don't think they're going to do the pool scene. Yeah, you'd better call Clunk and Peanut.